In this video, we're going to try and take a molecular formula, N2O4, all the way to a Lewis structure, to, I guess, the geometry of it, and then 3, does it have a dipole moment, or what's its, I guess, what's it look like in terms of being polar or non-polar. So the first thing you want to do when you're looking at a molecular formula is to determine the number of valence electrons. So to do that, we're going to take nitrogen in the periodic table, and if you start at lithium and put your finger on lithium and count that as 1, you walk over to nitrogen, it's 5 steps. He has 5 valence electrons through which he can make bonds. He can't use the inner electrons, but just the valence electrons. And oxygen has 6. So what we can do is say 2 times 5 is 10, and the 4 times 6 is 24. So we have 34 electrons that have to make it into this structure because they're on the outside. They're used for bonding, or they're going to be left as dots. The second thing you need to do is find the frame and fill in. So filling in the frame has to be made using the elements that have the greatest need. So they're typically going to be the ones that are furthest to the left on the periodic table, or if there's 2 that are the same, pick the one that's lowest. So sulfur, for example, instead of oxygen. But ours is nitrogen. It's 1 step over from oxygen in the periodic table. So this one's in the middle, and I had 2 of them, so I just put them both in the middle. Now we're going to add the other elements around our frame. And if I do just this, this is now our frame complete. I can sort of determine how many electrons have already made it into this frame from the 34 that I have. 2, 4, 6, 8, 10. So I need to add 24 more as I go to the next box. So we're finding the center, framing around it, and we're going to fill in with electrons and drop if we need to. So I'm going to maybe leave this last step for our final structure, our Lewis structure that's going to be valid. So filling in, we do it from the outside to the inside, meaning the oxygen's first. So that's going to take me a while, but let's sing the song to get started early. 2, 4, 6, 8. Who do we appreciate? Yay, you're done with that one. 2, 4, 6, 8. You're done with that one. Doing it from the outside again, from the outside in. 8. We stop there, and I'm just going to go ahead and put them all with electrons around them and then count to make sure I have 34. I needed 24 more, and I'm pretty sure I got that because for each of these oxygens I put 6 dots around it, 6 dots. Well, there's 4 oxygens, so 6 times 4 is 24, and we are done. Now you can count that to make sure. We got 8, 8, 8, and 8. That's 32, plus this one, the bond in the middle. Remember, bonds are like handshakes. There's 2 electrons in every line. Now drop it. Now this is where I have to say I need to satisfy these nitrogens, but we want to notice that we can do it a couple of ways. I'm going to just use dash. For this was one way. We could come down to this nitrogen to satisfy him, or I could have come from the north. Now you're not going to pick, typically you would draw all structures to get a better view, but I'm just going to ask that you remember we could have dropped from the north. We're going to come in from the south. But I could have again come in from the north with this oxygen that's up here. And in the same way, I could come from the north here, or I can come in from the south. It can't be both because I don't want to put more than 8 electrons around this nitrogen. I'm just going to come in from the north and draw this as our valid Lewis structure. There would actually be 3 more where we've considered these across from each other, these across from each other, over here, and then down here. So actually that's 4 more. 1, 2, 3, 4. So there's a total of 5 different resonance forms, but I just drew one of them. One of these. That's a valid resonance form, and I had to choose some dropping, and I just realized I have a resonance form. But let's go ahead and set the charge. I know these nitrogens have more than the number of bonds they want. We had to do that to get them to 8. You can't leave them with 6. So 2, 4, 6, 8, they have 8 electrons around them, but they have 4 bonds around them. And nitrogens and oxygens that have more bonds than what they want, they're going to be positive. So this one's also positive. And the oxygens that have less bonds, and nitrogens, if they have less bonds than what they want, they're going to be negative. And oxygen likes to have 2 bonds like we have here. Forgot his dots. And I think I have too many dots there. So we had taken these 2 and brought them down. He only has these 2 left, so that was a mistake. But we've got it fixed now. But this oxygen would have a negative charge, and so also with this one. Why? Because he has only 1 bond. He still has 8 electrons around him. We just need to remember he's negative. And I came in, again, from these oxygens to give a double bond. But I could have come in from these oxygens. So this is 1 resonance form, 2nd resonance form, a 3rd resonance form, and a 4th resonance form. I think I said 5, but I think we got 4 resonance forms. Crisscross, crisscross, same side, same side. That's 4 ways. 1 of 4 resonance forms. So we're going to stay with this and now just answer the question, forgot, geometry and dipole moment. Now the geometry around the nitrogens is key. Is it linear, the groups off the nitrogens? Is it trigonal planar or is it tetrahedral? I hope you're saying trigonal planar. These nitrogens each have 3 atoms off of it. This one has 3 atoms off of it, and this is connected to 3 atoms. So we'd say the group number is 3, it's trigonal planar, and what that means is you have 120 degrees between each of these bonds. And last but not least, we have bond polarity, certainly because we have a formal positive charge and negative charge, but because these negative charges can sort of be expressed in both places, -1/2, -1/2, and -1/2. I just had chosen this resonance form where the negative charge is here, but because we can have a mix of all those resonance forms, this actually is a 0 dipole moment because the symmetry of the negative charge around the positive charge. So highly polar in terms of bonds, but overall non-polar. That's pretty cool. Has a lot of bond polarity within the bonds. There's some separation of charge, but because these negatives are symmetrical around the positives, then we have a 0 dipole moment overall, a cumulative overall dipole moment of donut. So I hope this helps. It's a tough one. We're going to do 3 more like this, building the frame, filling in with electrons, dropping down when we need to, and determining the geometry and whether it has a dipole moment. Bye-bye.